All right, let's just jump right in. For decades, there's been this one monster of a question lurking at the heart of computer science and math. Does P equal NP? Now, it boils down to something that sounds super simple, right? If you can easily check if an answer is correct, does that mean you can also easily find that answer in the first place? But trust me, this isn't just some dusty old academic puzzle. It's one of the most profound and difficult questions in all of science.
But here's the thing. Answering it has been anything but simple. For more than half a century, the smartest people on the planet have thrown themselves at this problem, and they've all been stopped dead in their tracks. It's like the question itself has built this impenetrable fortress around it, made of mathematical walls that make all our usual tools pretty much useless.
And these walls, they actually have names: the relativization barrier, the natural proofs barrier, and the algebraization barrier. Each one of these represents a whole category of proofs, a whole style of attack that we now know for a fact cannot solve P versus NP. It proves that a huge chunk of our mathematical toolkit is just fundamentally too weak for the job.
So what do you do? If you can't break down the front door, you've got to find another way in, right? Well, researchers realized that to get past these barriers, they had to stop trying to force it. They had to change the very language of the problem itself.
And this is where things get really cool. This new approach is called descriptive complexity, and it completely reframes the whole thing. So forget about computers for a second. Forget about how long an algorithm runs. Instead, what if we ask, how complicated of a logical sentence does it take to just describe the problem we're trying to solve?
This slide just lays it all out perfectly. On the left, you've got the classic P versus NP, all about computation time on some theoretical machine. But on the right, that's the translation. Thanks to some huge breakthroughs, we know that NP problems can be described with a really powerful, complex type of logic. And P problems, they get a simpler, more restrictive logic. So the P versus NP question isn't about computers anymore. It's a language problem. Are these two ways of describing things actually the same?
Okay, so once you've changed the problem into a question about logic, you can start using some really wild tools. We're talking about bringing in a new weapon from the stranger, more abstract corners of mathematics.
Now, I know this is going to sound like something out of a sci-fi movie, but stick with me, because it's a real mathematical idea. What if, to really push these two logical languages to their limits, we didn't have to stay in our cozy, familiar world of numbers? What if we could jump into a different mathematical universe, one that has numbers bigger than any number you could possibly imagine?
They're called non-standard models. And yeah, you can totally think of them as a glitched reality. All the normal rules of math still apply. 1 plus 1 is still 2. But these universes also have these impossible numbers, these non-standard integers that are literally infinite. It's in these bizarre worlds that you can really stretch logic until it breaks.
So why are we doing this? Why travel to this bizarre mathematical dimension? Well, here's why. Because in these strange models, that enormous abstract P versus NP problem, it shrinks. It boils down to one single focused question.
This is the new mission. The whole epic quest for P versus NP now comes down to this. You build a special kind of network, a graph, that's infinitely large because you build it using one of those non-standard numbers. And then you look for something very specific, a hidden clique, basically a secret club of nodes where everyone is connected to everyone else. The real question is, can the powerful NP logic see this club, while the simpler P logic is completely blind to it?
And boom, here it is, right from the paper itself. I mean, look how specific this is. We're not talking in generalities anymore. We're talking about a very specific kind of graph built from prime numbers, looking for a very specific kind of hidden group. The key takeaway, the big aha moment, is that we've turned this giant philosophical headache into something you can actually check.
And this, for me, is the most exciting part of the whole thing. This isn't just another cool idea. It's a plan. It's a literal roadmap for what to do next to finally, maybe, crack this thing open. And that's what makes this a potential game changer. It doesn't just say, hey, here's a thought, and then walk away. It lays out a clear research program. It's basically handing the baton to the next wave of researchers with a clear set of instructions.
So let's break down this plan. Step 1, you've got to actually construct one of these weird non-standard universes where you can prove the simpler logic fails to find the hidden group. Step 2, you need to figure out what extra rules, what new powerful axioms you might need to add to math just to make that universe exist.
And step 3, and this is really cool, you bring it all back home. You simulate this whole cosmic game of hide and seek on our own supercomputers to see what happens.
Now hold on, because if this plan actually works, if they can build one model where the simple logic fails and another where it succeeds, the fallout from that is just mind-blowing. It would mean that the statement P equals NP is independent of our standard system of mathematics. In other words, the answer might be unprovable. Not just hard, but literally impossible to prove one way or the other.
Just stop and think about that for a second. We've always thought of math as having one single capital T truth waiting to be discovered. But what if that's wrong? What if in one version of mathematical reality, P does equal NP, and in another it doesn't? The answer might not be a fact about our universe, but a choice about which universe we want to believe in. So yeah, this research is pushing us right to the very edge of what we even consider truth in mathematics. For 50 years, we've been slamming our heads against a wall, and now we might have found a path through, not to a simple yes or no, but to something much, much deeper. Maybe the ultimate solution isn't about computers at all. Maybe it's about the fundamental rules we choose to build our reality on.